Welcome to the last section of Chapter 10. We're going to look at choosing a convergence test from Section 10.8. In previous sections, we presented methods for determining whether an infinite series converges. And in some cases, we discovered that it is possible to determine the exact value of a convergence series. In this section, we take a step back and focus on general strategies for classifying infinite series and deciding which tests are appropriate for specific series. It is helpful if you're already familiar with the convergent tests summarized in Table 10.4 that we're about to look at. With these tests in mind, we explore various strategies and illustrate them with examples. These strategies can be applied sequentially, more or less in the order in which they're given. And so this is a big thing, to use that table to kind of figure out which strategy to use. The other thing, this is the one formula sheet that I will allow you to use on test. You can use it in test 3, and you may use it on the final exam. Specifically, Table 10.4. There is a copy of this that you can download. You need to download the Word version that says, that this is the test 3 formula sheet. Again, you may use this on both test 3 and the final exam. I'm not going to walk through this because these are all the series tests and convergence tests that we've already gone through, but here is a nice summary of them and should assist you with this test, which tends to be one of the most difficult and challenging tests in this course. If you look in our learning management system, eCampus or Brightspace, you will find this download there for you to print a copy and use on the test. As always, when you're doing tests, make sure that you show both sides of all pieces of paper that you're using, in this case, the formula sheet. Do not add any notes or marks on the sheet prior to beginning your test. Let's look at our first example to categorize the series. So here we have a series, the summation from k equals 1 to infinity of 2 to the power of k plus cosine of pi k times the square root of k all over 3 to the power of k plus 1. So as we saw from the last section, 10.4, all the series and convergence tests tell what kind of series you have. So categorizing the series is really important to kind of use the tool that I'm allowing you to use on the next test, which of course is that table 10.4 that we just looked at. So in this case, a good step in analyzing this series would be to split it into two series by using a common denominator that we have here and creating two different rational expressions. And so if we split this into 2 to the power of k over 3 to the k plus 1 plus the series, the cosine of pi k times the square root of k over 3 to the k plus 1, we can see that we have both a geometric series first and an alternating series second. If you examine the table, you can see both the tests that we can use for each of these series. The general term of the first series is the ratio of exponential functions. So this one we can evaluate explicitly. What happens when k goes to infinity of this really basically rational expression of an exponential function as k goes to infinity? Because the cosine of pi k equals negative 1 to the k, remember that cosine goes between 1 and negative 1, especially at values of pi, right? Because this is the x value, remembering from trigonometry. We can see that the second series is an alternating series whose convergence can also be tested. Notice that for this entire original series to converge, both of these series have to converge, okay? So both the geometric series and the alternating series have to converge. It's a good test. Why don't you try and see if you can figure out if this converges or not. Next, we're going to look at example 2, the divergence test. Almost without exception, The divergence test is the easiest test to apply because it requires nothing more than taking a limit. Furthermore, it can lead to a quick conclusion, namely that the given series diverges. And so what this is insinuating is that this is a good place to start when you're trying to figure out which test to use and if a series converges or diverges, because this is one of the easiest to apply. So it might be a good starting place. So let's look at example 2, divergence test. Does the series, the summation from k equals 1 to infinity of 1 minus 10 over k all raised to the power of k, converge or diverge? We can see that the terms of this series alternate in sign for k is less than 10, because if k is less than 10, then the second subtrahend here, 10 over a number smaller than that, is going to be greater than 1, meaning that this number is going to be negative. And then because it's a negative number, as k increases, it's going to alternate in signs for, again, k less than 10. As soon as k becomes greater than 10, then this number is less than 1, 10 over 11, 10 over 20. And so 1 minus a number less than 1 is positive, and so will remain positive for all those continuing values. Applying the divergence test, we evaluate the limit of the general term using L'Hopital's rule and find that the limit as k goes to infinity of this function, of this series, is equal to e to the negative 10, which doesn't equal 0. Because the limit of the general term is non-zero, the series diverges, even though in this case it diverges really slowly. Okay? You know, this whole idea about applying L'Hopital's rule comes from Calculus 1. And just as a quick reminder as it applies to this problem, I've included this kind of annotation. Okay? So it's well known that e to the power of a is equal to the limit as n goes to infinity of 1 plus a over n to the power of n. Why is that? Because a equals the limit as n goes to infinity of n times the natural log of 1 plus a over n. And then using this set, we can then apply L'Hopital's rule to the limit of the natural log of 1 plus ax over x. Okay? So you can do some more background on that, but I'm not going to explain that in much more detail. But I just wanted to kind of show you how we went from this. It's just a general form of e to the power of a. Okay? Next, we're looking at special series in example 3. We've studied several special families of series that are readily identified and analyzed for convergence. Specifically, you should look for geometric series, p-series, and less obvious and less common telescoping series. Example 3, does the series the summation from k equals 4 to infinity of 1 over the 4th root of k squared minus 6k plus 9 converge or diverge? If we start with the divergence test, what we're going to find is that this is inconclusive for this series of positive terms. One approach is to rewrite the series in the following steps. Notice we can rewrite the denominator, since the radicand is a perfect square, as the 4th root of k minus 3 squared. Okay? If we then shift the index, making j equal to k minus 3, then notice we can do the summation from j equals 1 to infinity of 1 over the 4th root of j squared. If we simplify this, notice that what we get is the 4th root of j squared is the square root of j, or changing that index, we get the summation from k equals 1 to infinity of 1 over the square root of k. Now, hopefully you can recognize this as a p-series, but if not, just remember to rewrite the radical as an exponent, and you get 1 over k to the power of 1/2, which hopefully then is easily identified as a p-series. And since p equals 1/2, which is less than 1, then this series diverges. Integral, ratio, and root test. You've probably evaluated enough integrals by now to guess whether the general term of a series can be easily integrated. There are also some immediate clues. If a series involves factorials, something involving k factorial, or terms of the form f of k to the k, the integral test is not likely to help. On the other hand, series with terms of the form k factorial, k to the power of k, or a to the k power of k, where a is a constant, often submit to the ratio test. Okay? Does the series, the summation from k equals 1 to infinity of k squared e to the negative 2k, converge or diverge? The general term of the series of positive terms can be integrated using integration by parts, which reveals that the integral from 1 to infinity of x squared e to the negative 2x dx equals 5 e to the negative 2 over 4, which is less than infinity. Because the integral converges, the infinite series also converges. However, in this case, it's probably easier to apply the ratio test, and we find that the limit, as k goes to infinity, of the original function using k plus 1 substituted for k over the original function gives us e to the negative 2, the limit as k goes to the infinity, of k plus 1 squared, k plus 1 over k squared. And what we can see here is this limit is going to go to 1, k over k, and so we get e to the negative 2 times 1, which is approximately 0.135, which is less than 1. Because the ratio of successive terms is less than 1, the series converges. Okay, so there's two different tests that you can use, one a bit simpler than the other. And so again, you've been doing a lot of these, and now you're going to be doing them all at the same time, so you've got to figure out which one to use. And again, that's why I'm allowing you to use the table from 10.4. The last thing we're going to look at in this section is rational terms. If a series involves a rational function, or ratios of roots or algebraic functions, then a comparison test is a likely candidate. When the ordinary comparison test does not work easily, the more powerful limit comparison test may lead to a conclusion. As shown in the following example, analyzing the end behavior as k goes to infinity of the general term is often the trick needed to find a good comparison test. Example 5, comparison tests. Does the series, the summation from k equals 2 to infinity of the cube root of k squared minus 1 over k to the 4th plus 4 converge or diverge? The divergence test is inconclusive. Pulling out the integral, ratio, and ruling out the integral, ratio, and root test is impractical. We are only left with the comparison test. The end behavior of the general term is determined by working with the leading terms of the numerator and denominator, and we find that for large values of k, the cube root of k squared minus 1 over k to the 4th plus 4 is approximately equal to the cube root of k squared over k to the 4th. And we can simplify this into 1 over k to the 2/3. Therefore, a good comparison test is the summation of k to the negative 2/3, which is a divergent p-series. The ordinary convergent test is difficult to apply in this case, so we turn to the limit comparison test. Taking the limit of the ratio terms of the given series and the comparison series, we find that the limit of the cube root of k squared minus 1 over k to the 4 plus 4 over k to the negative 2/3 is approximately equal to, well, this is just doing algebra right now, right? I just went blank, sorry. So when we have the cube root of k squared minus 1 over k to the 4th plus 4, notice because this is a negative exponent, this is now k to the 2/3, which of course is the cube root of k squared. So we can go ahead and multiply these two terms, thus getting k to the 4th minus k squared in the numerator of this left function, okay? And then remember, we can apply the limit inside, and we can solve this limit by dividing by the largest power of k in the numerator and denominator, and we get this simplified term. And then as k goes to infinity, we have 1 over infinity squared, which of course goes to 0, 4 over k infinity to the 4th power, which goes to 0. And so we just get the cube root of 1 over 1, which of course is equal to 1. And because this value of L is between 0 and infinity, and the comparison series diverges, the given series also diverges. And so this is just, these are similar to some problems we've seen earlier in the text, but trying to figure out which one to use, again, is a challenge. And again, I'm allowing you to use the table from this section to kind of help you look at all of the tests on convergence and divergence.